Welcome on this physics section. So today we're going to be talking about aerodynamics. So aerodynamics is a study which focuses on the motion of air, in particular with interaction or with a solid body. Okay. So now we all know that air acts like a pressure, right? And the pressure is expressed in Newton per meter squared. When we see meter squared, we see that we're talking about an area. We're talking about an area, right? So which means if we have to calculate the force which is given by pressure multiplied by area, then the bigger is your area, okay, the bigger is your force. Meaning, if we had to have a door somewhere here, if a door presents a bigger surface, then a bigger force will be applied on the door. And the other end, if a door presents an angle, okay, they say an angle there on the side, then the lesser force will be applied on the surface, knowing the surface is given by the height multiplied by the length. Right. So now we want to talk about what happens when a vehicle is moving. Okay. So we've realized that nowadays they've tried their best, engineers, technicians, to give an ideal shape to our vehicles in order to reduce the force of drag. The force of drag is the force that is applied on a vehicle. It can be a car, it can be a plane or whatever that is applied on a vehicle in motion by air. Okay, by air, and then it's given by 1 divided by 2 multiplied by the area of the object moving, thus multiplied by the mass volume of air, okay, thus multiplied by the coefficient of drag, okay, the drag coefficient, if we can call it that way, and thus multiplied by the speed squared. Okay, so this is how you get the force of drag, right? So now we realize that the coefficient or the dragging coefficient varies according to the shape of the body or the considered body in motion. And the more your surface has, the bigger angle your surface has, the lower is your coefficient of drag. Okay, so if you can check that surface, it looks like an egg. Okay, so the more you approach the shape of the egg, okay, the lesser is your coefficient of drag. The lesser is your dragging coefficient, right? And after long studies, what happened? Like technicians, engineers have been trying to reduce the force of drag, and it's been happening that the coefficient of drag from those cars that we constructed in the ancient days, from 1920 up to somewhere 1930, 1920, the coefficient of drag was somewhere there between 1 and 0.7. And since 1990, okay, up to now, the coefficient of drag is being there somewhere between 0.4 to 0.2. Alright, so this now I'm having an example with two vehicles having the same power of the same engine power. So let's consider that this car was made in 1920 or somewhere there, but the engine is a good engine. So this engine can go up to I don't know, 180 or 200 kilometer per hour, the same as that one. Okay, let's consider the same condition of the road. Let's consider the same engine power. Let's consider the same weights on our vehicles. Okay, yeah, let's consider these things besides the shape, beside the surface. Okay, all right. So if I consider the first example here, considering that our height here, okay, is 1.6 meters. Okay, and our length, our tangential length is 1.5 meter. The surface of the car is given by 0.9 multiplied by the height, the maximum height, times the length. This, which means we're going to have 0.9 multiplied by 1.6 multiplied by 1.5, and then I'm getting 2.14 meters squared. Right. And considering this shape according to the chart, so if you want, you can go on internet or Google somewhere there, you're gonna get the chart of the coefficient of drag. Okay, so according to this shape, so we have that shape there. Okay, if there is coming that side, we have this shape. If there is coming that side, this shape is almost the one that we're having there. We're having that shape there. Okay, that shape there, like the one that we're having there is coming this side, and then this one here is 0.2. The coefficient is 0.2. So if we have to get the force of drag now, how we're gonna get it is we're gonna take 1/2 times area times the mass volumic times the coefficient. Now we need to know that rho here, which is the mass volumic of A, is 1.2 kilogram
per meter cube.
And then let's consider our vehicles, both of them are having a speed of 130 kilometer per hour. Alright. Okay, so in comparison to the A, okay, so if I can compare their speeds to the A is 130 kilometer per hour. And then if you have, we all know that speed is given in meter per second, which means 130 multiplied by 1,000, okay, to make it kilometer, to make it in meter, divided by 350,600, okay, and this gives me 36.11 meter per second. Then our force here will be given by 1.2 multiplied by the mass volumic of A, which is 1/2 multiplied by 1.2, which is the mass volumic of the A, multiplied by the area, which is 2.4. Okay. Now that should be 2.16, sorry, which is 2.16. Okay, and thus multiplied by the coefficient of dragging, which is 0.2, and thus multiplied by the velocity, sorry, the speed, 36.11 squared, and this gives me the force is equal to 338 Newton. Okay, this is for the first example. So let's consider our second example. Okay, so now let's consider our height here being 1.7 meter and our length being 1.4 meter. So in this case, the surface of the area will be given by the same formula, 0.9 times height times length. This will be equal to 0.9 times 1.7 times 1.4. This gives me 2.14 meter squared. Okay, so now if I have to calculate the dragging force here, so the dragging force will be equal to 1.2, so that is the first case. The second case, 1/2, sorry, multiplied by 2.14 multiplied by, it's almost, the area is almost the same, multiplied by the mass volume of A, multiplied by 1.2, thus multiplied by the speed, 36.11 squared, and then this multiplied by the coefficient of dragging, which is 1 in this case, equal to 1. The first time, in that case was 0.2, but in this case, it's equal to 1. So now, we realize that our force is equal to 1,674 Newton. Wow, what a difference. What a difference. We realize that this shape here gives more or a bigger surface to the air to pressure the car or to resist the movement of the vehicle. Okay, and you should know that the force of drag is actually constitutes an average of 65% of all the force that resists the movement of the car, besides the friction, besides all of that. So if we put everything together, the friction force, everything, the lifting and weighing force, all of that, 65% of the resistance comes from the force of drag. So you need to make sure, we need to make sure about our force of drag if we have to conceive a vehicle. Okay, that's why nowadays our engineers and technicians are doing their best to get the ideal shape in order to reduce the force of drag. And the ideal shape so far that we know of is the egg shape, an oval. Okay, so you can see that. So this is the oval. Okay, and then A comes here and there, here and there, here and there. Okay, so it tries to penetrate through the air so that the force would be minimized. Okay. Okay, so it was a pleasure of mine sharing this video with you.
Hello, wanna find out if buoyancy force is applicable in A or Archimedes principle? Then what you have to do is simple. Just watch this video and from there you're gonna judge by yourself. Cheers.
Hi. So is Archimedes principle applicable in A? Let's find out. So I have in front of me 3 balloons, among which 2 are full of helium and 1 full of air. So I'm going to release this balloon and then we're going to see. We know that Archimedes principle states that any object which finds itself in a liquid undergoes a force which is applied vertically upwards on the object which is found in the fluid. So now I'm going to release this balloon and see what's going to happen. Okay, so if I have just to break it down for you. So Archimedes principle states that. So if an object has a density, this is the density of the object, which is higher than the density of the fluid, then the object will sink. And then if the density of the object is equal to the density of the fluid, then there will be equilibrium. And then if the density of the object is lower than the density of the fluid, then the object will float. Or it will go high. So now I have these balloons here. I want to put them aside. So we all know that helium has a density. Helium has a density of 0.18 gram per liter, and A has a density of 1.2 gram per liter. So we can see that the density of helium is lower than the density of A. So now this balloon here, we can say that it has 95, somewhere there above 95%, which is helium, and then somewhere there between 5%, which is the density of our plastic, which is the body of the balloon. So you can see that helium has a higher percentage, which in return I can just say this is just helium. So at the end, given that A has a higher density, so it puts a force on the balloon, and which in return makes the balloon what? Float or go higher. So now, knowing that A is what is behind all of what is happening, so if we can just take out A from this space, so we're gonna create a perfect vacuum. So in a perfect vacuum, any object despite its mass, so if I take two objects, one, let's say, is just a stone or a piece of steel, then I take a lighter object like a feather, or what can I say, like a leaf of a tree. So if I take these two objects, I hold them at a certain height, from the ground. Once I release these two objects at the same time, I ensure you that they're gonna hit the ground at the same time. Yes, of course, with the speed of the acceleration of gravity. Alright, if it's in a perfect vacuum. Okay, so then this means that all the time that you get your mass from the scale, which says that you have, maybe you are 70 kg. Alright, so out of that 70 kg, you should know that the air has taken its part. We know that the density of a normal human being is 1062 gram per liter. 1062 gram per liter. That is a density of a normal human being. So at the end, if you want to get the volume of a normal human being having 70 kg, then what you have to do, you have to say volume is equal to the mass divided by the density. Then we're gonna be 70 divided by let's put this in gram as well, because that is in gram. 70,000 divided by 1062 gram per liter. That will be gram. That and that will go. So now we know that the force that is applied by the air or by the fluid or gas, in this case which is A, will be given by volume of the object multiplied by the density of A. Okay, so this will be in kilogram or in gram. If you want to put in Newton, then you have to multiply by G, the acceleration of gravitation. So now, if I want to get how much pressure or how much force is applied to a normal person weighing 70 kg, so now the force will be in gram. It will be here force of Archimedes, that's what we call it. Force of Archimedes in, let's say, mass of Archimedes in gram. So this will be then 70,000 divided by 1062, then this will be volume, and thus multiplied by the density of air, which is 1.2. And then at the end, what I'm getting here is 79 grams. So you should know then. So if your scale is telling you that you weigh 70 kg, then you have to know, you have to put in your mind that actually you are in 70 kg, 70.079 kg. Yes, in terms of percentage, that is low, but it's relative. Okay, it's relative in terms of what is your mass. So if you have a lower mass, which means the force of Archimedes is higher. I don't know if you get my point. Okay, I don't know if you get my point, because at the end, in terms of percentage, it will be high. It's not going to be low. So here, it's going to be lower. Sorry. So here, in terms of percentage, then I'll get 79. This multiplied by 100 divided by 70,000. Then I'm getting 0.112%, which is in return is lower than the what can I say? The tolerance which is applied to normal scales, nowadays. Okay, because I think the tolerance is somewhere there 1%. I think so. This is lower, so it's there. So actually, then this was a previous man showing this video, so you have to remember them. So air is for this space, what water is for the ocean. So which means if you remove air, this space is like removing water from the ocean. So as soon as you put the boat in your ocean and there's no water, which means then the boat will touch the bottom of the ocean as soon as you put it. By creating the perfect vacuum, actually what you're doing is you are removing air. So I ensure you then again that this balloon that you're seeing floating in air will hit the ground as soon as possible. You release it from your hands because there is no air which gonna put pressure on it to go and float. Okay. Receive my greetings from wherever you are. So today I have a pretty small scenario for you. I'm good in scenario as well. So I want to talk about physics, just the basic of physics, about action and reaction. So today we have our friend here is named J. J is a lift user, right? So now he found himself on the ground floor. This is the ground floor, right? So you want to go to the fourth floor, right? So now in the left is attached the spring on the plank of the left, and then there is attached the scale, that is the scale, that is the spring. So J, before the lift starts moving or starts going up, realizes that his weight is 700 Newton. Okay, considering the acceleration of gravity of 10 meter per second square. So here, obviously, J mass is 700 Newton over 10 meter per second square, which is 70 kilogram. So now, as they want to go up, here is the reaction, considering the free body diagram here. Here is the reaction of the lift from the plank, which is P. And then here is the action actually of the weight of J. So P now as the apparent weight, P as the apparent weight is equal to, P is equal to the weight of J, plus the mass of J, this time multiplied by the acceleration of the lift going up, which is considered to be 1 meter per second square. So that since the lift is going up, so now our acceleration is positive. So here we go. Now the apparent weight is 700 plus 70 multiplied by 1 meter per second squared, which is equal to 770 Newton. As at the moment that the lift starts going up, J realizes that his weight has gone up by 70 Newton. He has gained weight in a few seconds. So what's happening is it feels heavy. It feels heavier than before. So now this is how it's happening, what you go through daily or weekly. So let's consider now this time J coming up from the fourth floor to this, from the fourth floor to the second or to the first floor. Now this is what's happening. The same P is equal to the same thing, weight of J plus mass of J times C, which is the acceleration. So this time, since the lift is going down, c is considered to be negative, or -1 meter per second square. So now this is what we're getting. So we're getting 700 Newton plus, what is that? 70 kilograms times -1. So now this time around, J realizes that as it's going down, his weight is lessened by 70 Newton, which is 630 Newton. Actually, this is what we go through on a daily basis. So as the lift starts going up, the spring feels confined. As the lift is going down, the spring feels the same thing. Actually, it tries to release itself, but what's happening is the weight has changed. Actually, I would like you guys to understand this. So it was a pleasure of mine to share this video, and I hope that you guys are going to subscribe and you're going to like this. So don't forget to subscribe if you haven't. Don't forget to like if you feel like this has touched you, and don't forget to share if you want other people to understand what you just have understood. So for now, I'm going to ask you to take care of yourself, and cheers, bye.